Good morning, fourth grade. Just when you thought you were getting rid of Mr. Brewer, he's back again. This is not a mistake. We are on 8-2, so just keep that in mind when you're doing your journal pages and home links. We're going to be skipping around a little bit, so make sure that you are on the right journal page and home links. As always, get your math journal, math notebook, pencil ready to go. So today we are going to be doing real life angle measures as additive, which is another word for adding. Today's learning goal: apply your understanding of the additive nature of angle measures to real life situations. But as always, we will start with a warm up. So go ahead and complete these multiplication problems and then come check back. Okay, number one, you should have gotten 6/6 or 1 whole. The next one, you would have gotten 56/8 or 7 wholes. And the next one, you would have gotten 6/3 or 2 wholes. Go ahead and try these three. Check back when you're ready. The first one, you would have gotten 12/4 or 3 wholes. The next one, you would have gotten 20/10 or 2 wholes. The next one, you would have gotten 24/12 or 2 wholes. Let's go to these three. Check back when you're ready. Okay, the first one, 27/4 or 6 3/4. The next one, 32/5 or 6 2/5. And a big one, 500/100 or 5 wholes. Okay, boys and girls, this is your math message today, which is on page 273. I would like for you to try and complete these. I will read the directions to you. This is a warm-up, and then we will go over it. Find the missing angle measures. For each problem, write an equation with a letter as the unknown to show how you found your answers. So keep in mind, you need the answer, and you need an equation with an unknown. The unknown, by the way, is already given to you. So for example, number one, you'll use C as your unknown for the letter. Go ahead and check back when you're ready. Okay, number one, the equation that you should have written to get 115 degrees as your answer would have been 180 degrees minus 65 degrees equals C. And that's because we know this straight line right here is a 180-degree angle. And when we have a 65-degree angle here, we know that this must add up to 180 degrees. So we can subtract to find the unknown. Number two, we know that all the way around a circle is 360 degrees. So that means that we can use the equation 360 minus 270 to find the missing letter, which is 90 degrees. Number three is very similar to number one, knowing that 180 degrees is a flat line. So R is going to be 20 degrees, knowing that we can do 160 plus R equals 180 degrees, or you could have done 180 minus 160. There are a couple ways to do the equation. Number four is very similar again to number two. You would have gotten 90 degrees this time. 360 minus 270 equals P. Number five, this is a 90-degree angle, the chair itself, so you know that you're going to be using 90 degrees to help solve this problem. C is our unknown. We should have gotten 25 degrees because 90 minus 65 equals 25 degrees. And last but not least, again, we're going to be using 90 degrees. We're looking for the unknown letter here, I, and we know that 90 minus 45 equals 45, or 45 plus something gives us 90 degrees. Okay. What else in real life are angle measures used for? Well, Mr. Brewer can tell you from his own experience. I don't know if this is going to come up or not, but Mr. Brewer likes to do woodworking, and when I do that, I need to make sure that my angles are good to go, because if I am cutting a piece of wood to fit inside my house and it is not perfectly lined up, there are going to be gaps, and that would not be good. So one thing that I use is it for woodworking. Think about other ways that you'd use angles in your real life. Another way I'm thinking is if you are shooting a hockey puck against a wall, you need to know how it's going to come off. Is it going to come off at a 90-degree angle? Do you want it to come off at a 45-degree angle? So these are things you might not think about, but you do use angles in your real life. Okay, today you will be adding and subtracting angle measures to solve problems involving real life situations. Angles can be found in many sporting activities. Oh, here comes hockey. For instance, when a hockey player hits a puck into the sideboards at an angle, the sides of the ice rink make up a straight angle. It bounces off at an angle. This is called banking the puck. The line the puck moves along can be thought of as separating the straight angle into 3 parts. Let's explore how this works. Now, this is something you can actually do with a penny, or if you have a small circular object. You can actually take a book that has kind of a thickness to it, and you can actually slide that penny to a point on it and see how it bounces off. Okay. In this example, you can see that if you draw a 45-degree angle, which is right here, and you draw another 45-degree angle, which is right here, and you put the penny on the paper and fling it against the back of the spine of the book, it should go directly off on this 45-degree angle, like so. If you would like to try that, read the directions here and then try it on your own. So you would have noticed that it stayed on the same ray and banked off at a 45-degree angle. So we know that the angle that we flicked the checker at the book or the penny or whatever it was 45 degrees, and it bounced off at another 45-degree angle. What conclusion can you draw about banking an object off the book? The checker bounces off the book at the same angle at which it hit into. Hockey players bank passes off the boards according to this observation. As you can see in this picture, you are noticing. Now this is a different problem. It says 2 hockey teams, the Jets and the Stars, are playing each other. Jets player A wants to pass the puck to Jets player B, but a Stars player is blocking the path to player B. You can see him right here. Jets player A hits the puck toward the boards at an angle measuring 35 degrees. What is the measure of the angle formed as the puck travels around the Stars player? So we are looking for this angle in the middle. We know that if this is 35 degrees right here, that he is hitting the puck at, it's going to bounce off at 35 degrees as we learned before. So we need to figure out what this unknown is in here. Write an equation with a letter for the unknown to show your solution. Go ahead and try that on your own and see if you can get the correct answer. So the correct answer is 110 degrees, and let me explain why. You know that this board is 180 degrees. We also know that this right here is 35 degrees, and this is 35 degrees. So you need to subtract this 35 and this 35 to get what's remaining in here, which is a total of 110. Now, if you set up your equation and said 180 minus 75, or excuse me, 70, you would also be correct. Let's try it again. Stars player A wants his team to score. He purposely misses the net and banks the puck off the board directly behind the goal. The puck bounces off the boards towards star player A or B, who has an open shot at the goal. If the angle between Stars player A and Stars player B measures 100 degrees, so now we're talking about here is a 100-degree angle. What was the measure of the angle at which Stars player A banked the puck? So we need to figure out what was this missing angle. Well, we know that this is 180 degrees. We know that this is 100 degrees in here, so the total has to be 80 degrees between the two. But we need to divide that in half. So 80 degrees divided in half would be 40 degrees. Okay. Many different types of scientists also work with angles. For example, people who study eyesight are concerned with the field of vision, which is the angle that includes the area that can be seen without moving the head or eyes. So I want you to think about this. You're going to hold your index fingers in front of your nose, and then keeping your eyes and head fixed straight ahead. So you can't move your head, you can't move your eyes. Slowly move your fingers apart and back around toward each ear until you can no longer see either finger. So on your left hand, put your index finger up. On your right hand, put your index finger up. Put them out in front of you and slowly move them back towards your ears without moving your head and without moving your eyes. Eventually, you will start to not see your index fingers because without turning, your eyes cannot see behind you or really back to the left or back to the right without moving your head or eyes. Okay, this is called your field of vision. The area outside the field of vision is called your blind area. So this is where you can't see without moving your head or eyes. Now, keep in mind, here are some animals that have different fields of vision. So a human, we can, without moving our head and our eyes, we can see 180 degrees. We can see to our left, to our right, straight in front of us, all of that, but we can't see behind us. An owl can, yes, turn its head all the way around, but when it's just staring straight ahead, it can only see 110 degrees. So it doesn't have as much vision area or field of vision as a human. Now think about a rat. Take a look. A rat can see 200 degrees. That's a little bit more than a human, so it can sort of see a little bit backwards. Now, we're going to use this chart right here on page 274 and do some addition and subtraction to find the field of vision or the blind area. So take a look at some of these animals. What do you notice about the horse? Look at the field of vision for a horse. Think about why this might be. Where are the eyes located for a horse? A horse can almost see all the way around, 357 degrees. That is incredible. 360 degrees is all the way around. So a horse knows when you're sneaking up, either by hearing it, but most likely by seeing you. That is crazy. So here's how we're going to figure all of this out. We know that all the way around our heads is 360 degrees. So a human can see, without moving your head or eyes, 180 degrees. That means our blind area, to solve that, we would take 360 minus 180, and we would get 180 degrees that we can't see. I want you to fill in the rest of the chart. Go ahead and come back and see what you have found. Okay, for a fox only has a blind area of 100 degrees. It can see 260 degrees. And think about a fox's head is shaped sort of like a horse's. So its eyes are sort of on its top and sides. A horse only has 3 degrees for a blind area. Now, we're working backwards here. So a cat can't see 160 degrees, but can see 200 degrees. A dog can't see 120 degrees, but can see 240 degrees. An owl can see 110 degrees, can't see 250 degrees. A deer can't see 90 degrees, but can see 270 degrees. A Cooper's hawk can't see 60 degrees, but can see 300 degrees. A rat can see 200 degrees, but can't see 160 degrees. And a dragonfly, whoa, can see 360 degrees at all times. Can't see 0 degrees. So a dragonfly is certainly going to know when you are sneaking up on it. What is the greatest size a field of vision could be? 360 degrees, and we know that because that is a full rotation. Okay, I'm going to ask you to try this. I'll read the directions, and then you will go ahead and try this on your own. Okay, number 3, the field of vision of many animals, including people, is divided into a binocular field of vision and 2 monocular fields of vision. And the reason I said mono is because mono means one, and bino means, or bi means 2. So in the binocular field of vision, we can see an object with both eyes, hence the reason bi and 2. Binocular vision helps us see in 3 dimensions and tell how far away an object is. In the monocular fields of vision, we see things with just one eye. The diagram shows approximate fields of binocular and monocular visions for different animals. So let's just work through this with a human. So with a human, we can see 140 degrees in front of us. But with just our left eye, without moving our left eye or without moving our right eye, we can see a certain amount of vision to our left and a certain amount of vision to our right, equally on both. So knowing that we can see a total of 180 degrees in front of us, which you can see right here, that means that we can see 20 degrees on our right side and 20 degrees on our left side, because 140 to get to 180 means that we're missing 40 degrees on our left and right, and we have to divide that number in two. You can see with a sheep, for example, a sheep can see 62 degrees in front of it, but uses its left eye for some of it and its right eye for some of it. The fox can see 40 degrees with both eyes in front, but uses the left eye for a lot and the right eye for a lot. So we have to figure out, knowing the total field of vision, what is the left and right eye, which you're going to be doing down here. Now we just did the first one together. We can do the second one, and then you're going to pause the video. So I always look to see if they give us a total field of vision, which they do for this one. And that means that in front, they can see 62 degrees, and on one side, they can see 104 degrees. So knowing that the left and right are the same, this one, I can just copy 104 to the right side. So it's 104 degrees. Now, you are going to go ahead and try and solve the rest on your own, and then come back when you're ready. Okay, for the fox, the total field of vision, we just needed to add up all of these numbers and got 260 degrees. Same thing with the rock dove, which was 320 degrees. Now with the horse, we're just missing the left side, which we can just copy from the right side, which is 146 degrees. The cat, now we're looking for just what it can see with both eyes in front. We know that it can see all around its head 200 degrees, and on the left side and the right side, it can see 30 degrees each. So that's 60 degrees. So we need to subtract 60 degrees from 200 to get 140 degrees, which it can see straight ahead. The harbor seal, we can see 209 degrees. The dog, its right side is going to be 90. And then the owl, same thing that we did with the cat, it can be 70 degrees. And last but not least, the red-tailed hawk can see 279 degrees. Okay. We're going to change gears on page 276, and I really like these diagrams because they make you use the data. It says the table below shows the approximate distance in miles between downtown areas of different towns. Use the information to solve the following number stories. Show your work on a separate piece of paper. Okay. We'll do number one together, and then you're going to try 2, 3, and 4. So just looking at this, I can see this diagram is talking about from Deerfield to Glencoe, it's 8 3/10 of a mile. So you notice how I'm using the left-hand side and the right and the top to go ahead and tell me how far it is. So it says, what is the distance from Glencoe? Okay, so I'm going to go to Glencoe over here, to Highland Park and back. So that means there and back. So if I go to Glencoe and I scroll over until I get to Highland Park, which is right here, it takes 4 1/10 of a mile to get to Highland Park, but remember, we're going back. So our number model would either be 4 1/10 plus 4 1/10 equals H for Highland Park, or 4 1/10 times 2. They chose to do the multiplication, which might be something that you choose. The correct answer that you would get would be 8 2/10 of a mile. Between which two whole numbers is this? Well, it's a little bit more than 8, but not quite 9. So it's between 8 and 9. Go ahead and try number 2, 3, and 4 and come back when you're ready. Okay, number 2 says Dr. Isaacs drove from Wilmette to Highland Park and back, again, and back, on Tuesday, and again on Wednesday. So that's 4 times he drove to a spot, okay, because it's and back. How far did she drive altogether? So we know that we're going to be multiplying by 4, but we need to know what. So I'm going to go to Wilmette and then go to Highland Park. 10 1/10 looks like we're going to be timesing by 4 because there and back twice. You're going to get 40 4/10 of a mile, which between 40 and 41 miles. Number 3, Professor Lee lives in Park Ridge and works in Deerfield. He drives from home to work and back Monday through Friday. That's 5 days. How far does he drive each week? Now keep in mind 5 days, but in those 5 days he does it twice because he's going there and back. So that's 10 times. So that means to Park Ridge, right here, to Deerfield, right here, 13 and 6 tenths times 10, which is going to get us 130 60 tenths, which is the same thing as 136 miles. Try this. If you tried this down here, it says Officer Wells drove back and forth between Northbrook and Deerfield once every day for a few days. At the end of that time, he had driven 40 and 8 tenths of a mile. How many days did he do this? You're almost working backwards on this. So your number model would be T times 6 and 8 tenths, because it's 6 and 8 tenths from Northbrook to Deerfield. And if you know, it would be 6 times 6 and 8 tenths, which would get us 40 and 8 tenths. But remember, it's driving there, and back. So you have to divide that number by 2, which gives you 3 days. That was a difficult one. Okay, on to math boxes. Go ahead and try and solve and come back and check what you got. Okay, for number 1, your 2 answers are shown. Number 2, your 4 answers are shown. Number 3, your 4 answers are shown. Number 4, there's your answer. Number 5, and number 6. Okay, tonight's homework is going to be defining the missing angle measures. For each problem, write an equation with a letter for the unknown to show how you found your answer. Remember to post a seesaw, and don't forget the bottom 7, 8, 9, and 10. I think this might be the last time you hear Mr. Brewer's voice for math. Have a great day.